about the properties and the properties of alumina. So, amongst the ceramics, alumina is the most widely used ceramic, and it's the most widely used ceramic because, well, it is the cheapest amongst the lot. It costs about 50 rupees per kg. This is the powder cost, okay? And the density is about half of that of steel. Ceramics actually are quite stiff. So if you look at the modulus of alumina, it is 410 GPa, and most of the ceramics have got excellent compressive strength. Okay, so you can see that a fully densified sintered alumina has a compressive strength of around 3 GPa, and even its bending strength and tensile strength are not too bad. They are very similar to that of low carbon steel. Okay, and so what are the different applications of alumina? Where is it that you have seen alumina being used? Where is it that you have seen alumina being used? Anyone? What are the what are the different kind of grinding grits that you are familiar with? Uh, can you unmute yourself? Are you able to hear me?
Yes, sir.
Okay.
Yes, sir.
So, uh, one of the places where alumina is used is in making the grinding grits. Alumina grinding wheels are very commonly used for grinding of steels. Okay, and they are also used. They are also used for making insulation panels. So the deal is that thermal conductivity of this 30 watt per meter Kelvin is for the sintered alumina, sintered and fully dense alumina. But if you have a lot of porosity within the part, then the thermal conductivity would come down considerably. Okay. All right. Next, the next ceramic that we are going to look at is silicon carbide. Okay. Now, silicon carbide, it has a density which is lower than that of even alumina. Once again, it has excellent modulus, and its compressive strength is also higher than that of alumina. The okay, amongst the ceramics, it has got a pretty decent fracture toughness of 4 megapascals, 4 MPa root meter. So, by the way, the fracture toughness of material. So, what is the quantity that is being specified? Have you heard means? Have you heard about? Do you know as to what quantities are used to characterize the fracture strength of a material? So for stiffness, we have elastic modulus or Young's modulus. For yielding, we have yield strength. So for fracture, what is the material property that is associated with fracture?
UTS, ultimate tensile
No,
strength.
UTS doesn't say anything about fracture strength, fracture toughness. So take glass for example. Okay, so glass has got quite a bit of hardness. If you subject it to a tensile test, it will have a pretty high value of UTS. But we know that glass is brittle. So what is used to characterize the fracture toughness of materials?
Hardness scale.
No. So,
The area
Heating.
under the stress strain curve.
Surface energy, sir.
no, no. So for fracture toughness is characterized by something known as critical stress intensity factor. Critical stress intensity factor K1C. Okay, K1C. Now, how many of you have heard this term, critical stress intensity factor? Not stress concentration, stress intensity factor. You haven't heard of it before? So, whenever, so if you have a, so let us say you have a plate. Okay, it's a large plate. Let us say there is a crack in the middle of the plate, and you're subjecting this plate to some far field stress. Okay, far field stress, and let us say this is 2A. Okay, now if the material is brittle, and let us say assuming linear elastic behavior, what will be the stress distribution? Means what can you say about stress distribution in the neighborhood of the crack? Okay, fine, we'll come to this fracture toughness business later on. Okay, so so basically what happens is, in the neighborhood of the crack, so if I take a coordinate system at the tip of the crack, okay, and if I take some point P at a distance R from the crack tip, then what happens is the stress scales as, so stress at this point, let me call this sigma naught. Okay, stress at this point scales as sigma naught root A divided by square root of R for a linear elastic material, a through crack in a plate. Okay, so
Sir, it's multiplied by 2 also, I think. 2
I
into
said
root A.
proportional to.
Oh, sorry, sir.
uh, so so we define something called stress intensity factor. Okay, so stress intensity factor in this particular case would be uh, just 1 second. It would be equal to, so we define something called stress intensity factor K1 as equal to sigma root pi A, and we say that the crack will propagate when the stress intensity factor exceeds the critical stress intensity factor for the material. So stress intensity factor is a effect of application of stress, whereas critical stress intensity factor is a material parameter. So what is being specific, and it has, what will be the unit? So look at stress intensity factor. So what will be the unit of stress intensity factor?
Pascal under root meter.
Pascal under root meter, or you can also have it as megapascals under root meter. So that is the reason that the stress, the fracture toughness is being specified as 4 MPa root meter. So it has pretty decent fracture toughness, and silicon carbide has got very high thermal conductivity. Okay, so it has a thermal conductivity of around 120 watt per meter Kelvin. What is the thermal conductivity of low carbon steel? What is the thermal conductivity of low carbon steel?
Sir, half of that of alumina, I guess 15.
Very good. So it has a thermal conductivity of around 50, 50 watt per meter Kelvin. Okay. What is the thermal conductivity of aluminium? What is the thermal conductivity of aluminium?
Sir, around 240.
It has aluminium would have somewhere around 200. Okay. Uh, yeah, around 240, 250. So the silicon carbide thermal conductivity is twice of that of steel and half of that of aluminium. Okay, and it has got a very high melting point. Its melting point is 27-30 degrees. What is the melting point of steel? What is the melting point of steel? Learn the thermomechanical properties of steel, aluminium, copper. Okay, they are very widely used. It is good to know these properties. What is the melting point of steel? All of you
Around
have got an
1500,
idea.
1500.
1375.
1500.
1500.
Okay, it is somewhere around 1400. It will depend on which alloy you are talking about. It will change a little bit. If it is pure iron, it is about 1440, and then it keeps dropping as you get into these alloys. So let us say it is about some 1400 degrees Celsius. So silicon carbide melting point is nearly twice of that of is twice as that of steel. And what is the melting point of aluminium? Roughly.
800 around.
No,
800
no,
degrees.
800 is very high.
660.
It is about 660 degrees Celsius. Okay. So in comparison to aluminium melting point, the melting point of silicon carbide is 4 times of that. Okay. So it has got a very high melting point. So one very interesting application where silicon carbide is used is actually in heating elements of furnaces. Okay. So I have shown a picture over here and I have marked with this arrow that typically it can be used to take the heating elements, means you can use silicon carbide heating elements for furnace temperatures of up to 1650 degrees Celsius. Okay, so if you want to melt steel, you need a furnace with this sort of a temperature. So metals can of course not really be used to go to these kind of very high temperatures. Okay, well, maybe I'll take my statement back. Normal metals cannot be used. So now thermal conductivity plays a very important role in being able to use silicon carbide for this heating element applications. Why do you think so? So one of the problems with heating element one of the problems with heating elements is that they would fracture if they are subjected to any sort of a thermal stress. So for a furnace, can you give me some simple examples of some physical events which can cause thermal stresses on the heating elements? Have any of you, how many of you have used a furnace or at least a oven? You must be having home ovens, right? Just raise your hand if you have used it. So all of you have used, na? So now imagine, like when you use these ovens, furnaces, okay? What sort of a action on your part can cause thermal stress on these heating elements?
A sudden increase in the temperature of the oven.
Sudden increase in temperature means normally you would have some heating rate. Heating is typically controlled and it would depend a lot on the power which the system would be able to accommodate. That is not really up to you. There are some limits to which you can go, and the designer sort of takes care of that. So some simple actions, like for example, you open the furnace door when it is like at its peak temperature. Okay, what will happen? You
Cold
are
air. Yeah.
basically subjecting it to a thermal shock. It is similar to when in peak summer, when you step out of an air conditioned room, what do you feel? You feel a thermal shock, right? You were exposed to some 20 degrees, 24 degrees up till some point, and suddenly you are exposed to 50 degrees of uh, air, and then you can feel the shock on your nostrils. Now imagine that for the furnace elements. They are subjecting the air to nearly 1500 degrees Celsius, and then you don't really think much, and then you open the door. What will happen? That 1500 degrees Celsius air will rush out. You may get hurt in the process, and cold air will go inside. Okay, so they'll be subjected to thermal shock. In the same fashion, if you open the furnace door when it is so hot, and then you place some part or something which is actually at room temperature, and if uh, if there is some sort of a contact between what you are placing and then the heating element, once again it can be subjected to thermal shock. Okay, now, so when they are subjected to thermal shocks, what will happen exactly? Why will the material break?
Sudden cooling.
There will be a large.
Sudden cooling. So why would it break?
Because of different elongation in different regions.
Very good. So what is happening is that where it cools, the material wants to shrink over there. But where it is hot, it doesn't want to shrink. So because of this differential, because of the thermal gradients, you end up generating thermal stresses within the material. And if these stresses are high enough and you have some micro cracks already present within the material, then the stress intensity factor will exceed the critical stress intensity factor, and you will have cracking or fracture of the material. Now, why do you think high thermal conductivity would help you basically reduce these chances of cracking?
The heat will be quickly distributed.
So,
The
high thermal conductivity materials are much better at maintaining thermal equilibrium, or are they are much better in diffusing the heat and reducing the thermal gradients which occur within the system. That is precisely the reason why you would prefer a copper bottomed vessel for cooking as compared to a stainless steel vessel. It can reduce the thermal gradients within the system. So high thermal conductivity and consequently high thermal diffusivity of silicon carbide along with moderate fracture toughness makes it a very good candidate for heating elements. Okay, so it is used in furnaces and
Yes,
yeah,
yes. So what
yeah.
exactly is the difference between the this thermal conductivity and thermal diffusivity in yeah,
So
in this
what
heat?
actually matters is not thermal conductivity. So for diffusion of heat, what is the parameter of relevance? Is it really thermal conductivity?
No, sir, that alpha term is important.
So what matters for means conduction of heat is thermal diffusivity. What is thermal diffusivity? So thermal diffusivity is basically equal to K divided by rho C. Okay, this is thermal diffusivity. Now in this particular case, K is high, rho is low. Okay, C is comparable, specific heat is comparable to other materials, so automatically this leads to high thermal diffusivity. So have you heard about something called diffusion time? Diffusion time, have you heard about this?
Yes, sir.
What is it?
Sir, so it is that time that heat takes to propagate, something like that is transient heat transfer.
So diffusion time is so diffusion time is square root of 4 alpha t. Sorry, diffusion length is square 4 alpha t, not diffusion time. Diffusion length L is equal to 4 alpha t. So it tells you how quickly heat is diffusing within the material. Okay, it depends on diffusivity and time. Okay, anyhow, so this is about silicon carbide. Now there is one application where this very high compressive strength and good fracture toughness really matters. um, so it really comes in handy for cutting tools, uh, grinding grit, and one application you may not think much about is for making armor plates. Okay, so armor plates which are made out of steel, um, they are not very effective in stopping high velocity, high energy projectiles. Okay, so there is some other failure mechanism at play, because of which bullets can this armor piercing bullets can cut through pretty thick steel plates. So using something like silicon carbide or alumina tiles, ceramic tiles, you get a couple of advantages. One is their density is lower. So for the same volume, the mass of these armor plates would be lower. And second thing is they have very high melting points. So means the heat which is generated during that impact is not going to soften the material. And third, they have very high compressive strength. So what this does, this high compressive strength, what it does is it ends up either deforming or fragmenting the bullet which comes and hits the tile. So that is the reason that for this armor plates of higher stenag number, there is some what categorization that you do: stenag 3, stenag 4, stenag 5, you want to get protection from. So for higher stenag levels particularly, you don't have any choice but to go with ceramic tiles based armor. Okay, next.
Sir,
Next, yeah.
sir, which one will be a better choice for armor, like polycarbonate or these ceramics?
Oh, ceramic. See, uh, ceramic, of course, is a much better choice for bulletproof, means bulletproofing applications. But two things. See, where is polycarbonate used? Polycarbonate is used wherever you need the transparency property. Okay, so like prime minister, chief minister, they are giving some speeches, they want some level of protection from bullets and stuff. So they put these polycarbonate panels in front of them. Okay, but they will not really be effective for protecting against see, even amongst the guns, depending upon the caliber of the bullet. Okay, the mass of the bullet, the velocity with which it is coming, uh, you need an armor accordingly. Okay, so if you are getting protection from a small pistol, a polycarbonate based armor may be sufficient for you. But if you are going to need protection from assault rifles, okay, or armor piercing bullets, then in that particular case polycarbonate will not work. So over there you will need much better armor, like for example tiles, ceramic tiles which are made out of alumina or silicon carbide. So what you will use will depend on what you are trying to protect yourself from. Okay, All right, next let us look at tungsten carbide. There are not that many ceramics, so don't worry. We are only going to talk about 4-5 ceramics. So next is tungsten carbide. Okay, so what are some of the properties which sort of stand out for tungsten carbide? One one of the things is it is dense. It is very dense. Okay, tungsten is a dense metal, and tungsten carbide is also dense. What is the density of steel? What is the density of steel?
There are around
8.
It is around 8 watt units.
8 grams per cc.
8 grams per cc. Okay, so tungsten carbide is nearly twice, no, actually exactly twice as that of steel. Steel is 7.8 gram per cubic centimeter. This is 15.6 gram per cubic centimeter. So it is twice as dense as steel. So it feels quite heavy when you hold it. It is very stiff. Okay, so its shape doesn't really change upon application of a force. It has very high compressive strength. Its compressive strength is even higher than that of silicon carbide. Okay, fracture toughness is decent, thermal conductivity is decent, similar to that of steel, and melting point is quite high. Okay, melting point is quite high. So do you think we will use tungsten carbide for armor? It has very high strength, even higher than silicon carbide.
No, sir,
No,
because
sir,
it's
because it
it
is
is
very heavy.
yeah, it's
Because it
dense.
is very heavy. Who is going to carry all this weight around? In fact, for most of the military products, so if you take a armor tank, if you take a, let's say, combat helicopter, fighter jets, whatever, weight is super important. You keep making things heavier, you need a much higher caliber engine, and you need to carry much more fuel. So basically the whole thing becomes like a big rock. So you can't really use silicon carbide for armor applications. Sorry, tungsten carbide for armor applications. Silicon carbide is way better than this because its density is nearly 5 times smaller than tungsten carbide. So where is it used, tungsten carbide? So one set of application where you are very familiar with use of tungsten carbide is ceramic inserts. Okay, so basically these are all tool inserts. Tool inserts. Okay, why do we call them as inserts?
They are usually braced onto some like mild or some other steel.
Yeah, very good. So they are either braced or bolted onto um, some tool holder. Okay, so that's why we call them as inserts. Now, so we'll use them for making yeah, tool inserts, either for turning, milling kind of applications. And then another place where they find the application uh, is in armaments. Okay, so why do you think they become a natural choice for armaments? So at least as far as I know, like they are used in this in bullets. Okay, so that is one application, and another application is, one second. Okay, that is one application, and another application is so see, there are many kinds of missiles which are fired, and one class is these kinetic energy projectiles. Okay, so in these kinetic energy projectiles, they use this tungsten carbide based um, projectile. What is the main advantage of using tungsten carbide based projectile in for these missile heads or bullets? What is the main advantage?
They won't rupture in case of high stress.
They have many advantages. First and foremost, see, weight is a problem for many applications, but weight is a main positive when it comes to kinetic and projectiles. Okay, because denser the more the kinetic energy it will pack. Okay, so that is one thing. Second thing is it has a very high melting point, so it doesn't soften upon getting heated or anything. It has very high compressive strength. So all of these properties make it a very attractive candidate for armaments. Okay, so tungsten carbide is used for these tool inserts and tools, and they are also used in armaments. Now, next, moving on to zirconia. Now, in zirconia, quite often it is a little amount of yttria is added, and this whole thing is called yttria stabilized zirconia. In short, it is called YSZ, yttria stabilized zirconia. Amongst these ceramics, the yttria stabilized zirconia has got a very low thermal conductivity and thermal diffusivity. Okay, now, so for this particular reason they are used in thermal barrier applications. So they are used in thermal barrier applications, and it has a decent amount of fracture toughness, compressive strength, flexural strength, and all of that. So if you take a look at this particular turbine blade, okay, if you take a look at this turbine blade, now over here, this white colored coating that you see is basically the thermal barrier coating, and you can see, uh, look at the temperature profile over here. So like what you see over here, this is the basic turbine blade material. Okay, so this is the super alloy, it's written on the top. This is the super alloy, and then this over here is the coating. This is the sorry, this is called bond coat. Anybody, what is a bond coating? Anyone has any idea? So ceramic doesn't really stick to metals. There is not much of a chemical adhesion between ceramic and metal. So if you deposit the ceramic coating directly on metal, it's not going to bond. So you deposit a intermediary coating called bond coating. Uh, so it is like if you want to stick something poster on the wall, what do? You first put some glue, okay, and then you stick your poster on the glue. So it is a bonding agent. Glue is a bonding agent. In the same manner, you put something called a bond coat. Bond coating material is such that it will bond well with the substrate, and it will also bond well with the ceramic coating. So you put the bond coat on this, and then finally you put your ceramic coating. So what do you see is the thickness of the ceramic coating? You'll have to zoom in a little bit, otherwise you cannot see. But anybody who can read the fine print, what is the thickness of the ceramic coating?
300 micrometer.
So this is
100
about,
to
means here in the picture it is given as 100 to 400 micron, but 300 micron is a good number. So it is only 0.1 to 0.4 millimeters. It's a thin coating, but then this thin coating can give you a temperature drop of nearly 100-150 degrees um, across the hot gases which are going over the turbine blade and the substrate material. Okay, so basically, uh, what is your overall objective over here? Why not? Why do you need all these coatings? Why not just operate at lower temperatures for the gas turbine? Why do you want to push the envelope of the temperature at which you operate?
So in thermal power stations, it can.
What is it? Can you repeat it a bit louder?
So it can be used in thermal power stations and.
No, that was not the question. The question was, why are you trying to operate at such high temperatures that you need protective coatings?
So if you want the turbine to move fast, then probably like the air will get heated with friction. So
The higher the operating temperature, the higher the efficiency of the system. You're trying to get more power out of the engine, and for that the operating temperatures need to be higher. But at such high operating temperatures, the metal cannot really retain its shape effectively. So it undergoes good amount of creep, so you provide this protective coatings. Okay, now next, moving on to the last ceramic that we are going to look at is silicon nitride. Silicon nitride has got a relatively lower temperature, so this gives us an means, so processing it is easier amongst the other ceramics, because the sintering temperatures at which you need to work would be lower for silicon nitride, and it has also got a relatively lower density. Okay, so 3.2 grams per cc, very close to that of silicon carbide. Now, one of the applications where silicon nitride is used is in making, it is used in making bearings. Okay, so for making ceramic balls and ceramic raceways. Now, what do you think would be the advantage of using a ceramic bearing over a steel bearing? Bearings that we normally use, we make use of steel, and I have even given you the grade of the steel which is used. So what do you think would be, what do you think might be the advantage of using ceramic balls and raceways over steel?
Sir, brittleness.
Huh?
Brittleness.
Why will that be an advantage?
Sir, low density.
Sir, low
So
weight.
it will make the bearing lighter.
Yeah, okay, the roller means so if you look at advantages, okay, so what are the advantages? Well, first thing is low friction, so frictional losses are lower. So what this allows you to do, so low friction, and then can operate at high RPMs. Okay, now what is the typical rotational speed for most of the motors, engines? What is the common operating RPM?
5,000 RPM.
Huh? 1000? Where did the number 1000 come from? What is the basis? So if you take induction motors, most of the motors that you see around you are all induction motors. So for induction motors, what would be the RPM? For a 4-pole induction motor? All of you have taken a electrical engineering course. So what is the RPM at which induction motors spin? They spin at about 1400 RPM. Okay, so I think 1440 to be precise. Let's say 1400. What is the typical engine RPM? Typical engine RPM is also somewhere around that 1000 2000 mark, engines can spin at higher rpm, but that's a typical rpm. What is the rpm to which something like a dc motor can go typically? Let's
Sir,
say
a B
brushless dc motor.
4,000.
Okay, so typically they can go up to, let's say 3000 is the normal thing. Fine. So let's say 3 to 4000 RPM. Now, can you name some applications where high RPM is used within the application? Some application where high RPM, high means I'm talking about something like, okay, so something like 100,000 RPM. Can you think of any applications where very high RPM is used?
Sir, I think aircraft, somewhere in blades of the aircraft, I think.
No, no, not that time.
Wind turbines.
I'm not sure about aircraft. Huh?
Wind turbines.
No, Baba, wind turbine is low RPM case. Where did no? So, have you you must have heard about micro machining, right? There is one micro machining center in our department. So whenever you go to lower dimensions, when you want to cut the material, you want to make a hole of 200 micron diameter, 100 micron diameter, to get the cutting speed to some decent value, the rpm needs to be very very high. Okay, so that is one application where very high rpm is used. Now, so if you go to something like 100,000 rpm and all, typically what you do is you go with something like either air bearing or magnetic bearings and all that. Recently, one application I have come across was a flywheel based a flywheel based energy storage system. Okay, in a microgrid. So I have seen that application where these RPMs are very high. Can you think of some examples where something like 20,000 RPM is used? That is also very high, but not high to the extent of 100,000 RPM, but 20,000 RPM. Any applications? Hmm? So one application which fascinates me quite a bit is so if you take the Tesla electric cars, so Tesla has become a gold standard these days for electric cars, and they their motors have very high power density, meaning if you take the power they can generate and divide it with the weight of the engine, that number is very very high as compared to what we normally produce, means whatever is the specific weight for our motors. Now, one of the ways they achieve that is they spin their motors at very high rpm. So the rpm in Tesla motors, they can reach up to something like 18,000 rpm, okay, which is nearly 5 to 6 times higher than what we typically operate at. Now, so whenever you operate at high rpms, the steel bearings normally are not really preferred. In those cases, you would prefer to go with something like, you would prefer to go with a ceramic bearing. So why do these two things go together, low friction and high rpm? Why is it necessary that your frictional losses be very low as your rpm increases?
To reduce heating.
To reduce the heating. Okay, otherwise what would happen is very quickly you can lead to some sort of a jamming or locking phenomena in the bearings. So this is one advantage, low friction, you can operate at high speeds. Second advantage is the stiffness of the bearings is low, stiffness is high. And third advantage is the uh, low weight. Okay, rolling elements weight is low. Actually, this rolling element weight matters quite a bit at high RPMs. Any guess as to why? So at higher RPMs, the centrifugal forces are quite considerable. Okay, and the centrifugal forces scale linearly with the mass of these elements, the rolling elements. So for this reason, actually having low density material for the rolling elements is quite a bit of an advantage. There is one more advantage which is a little non-intuitive, which is whenever you need electrical insulation within the system. Okay, so let us say you have some high voltage on the rotating shaft and you want to protect the stator or the stationary elements from the voltages. Then also you can use ceramic bearings. You can also use in electrical motors where you want insulation across the shaft and the outer casing. So for all these reasons, you use silicon nitride for making ceramic bearings. There are two kinds of ceramic bearings. One is a full ceramic bearing where raceways as well as rolling elements are ceramics, and there is another class where the rolling elements are ceramics but the raceways are made out of metal. Okay, so with this I complete the what I complete exposure to some of the um, plastics, metals and ceramics which we use in engineering applications. The objective of the last few lectures was to introduce you to some names which keep coming up in part means which keep coming up in material selection for parts. The class of materials which is currently available to you is enormous, but then if you are exposed to too many things you may not remember anything. So that is the reason that I just talked a little bit in detail of few of the materials which are used quite often. All right, next let us go to some math which is associated with material selection. Okay, now one of the things uh, which we do for quite a few applications is try to reduce the weight. Okay, try to reduce the weight of the system. Now weight reduction is important for several reasons. So what do you think is the advantage of reducing the weight? Let us start with some static structures. So let us say that you're building a bridge, for example. Now, what is the point in trying to reduce the weight of the bridge? You are anyhow not going to bear that weight. It will be finally going to the ground. So why do you care about reducing the weight?
uh, to put less stress on the beams of the bridges.
Self weight is only a part of the stress within the structure. Normally that is the smaller part. To some extent your answer is correct, but
So it is
that's
easier
not.
to construct,
Sorry.
easier to construct or assemble.
And we
So
should use as less as material as possible so that cost is also low.
so see, in business, bottom line is all that matters for the top management. Okay, so for the business to sustain, the cost of production must be low, and fine, you need to get as much price for your product as possible. Now to lower the cost of production, reducing the weight of the system is a very good strategy because it helps you lower the material cost, it helps you lower the handling costs, because well, heavier the things, the more difficult it is to handle them too. Okay, so uh, weight affects a lot of things, and by lowering the weight of a structure, you can basically lower the cost of your entire system. Now, there are two things that you initially start with to figure out as to what material would be a good choice if you want to reduce the weight of your members. So one is from stiffness perspective, and second thing is from strength perspective. Okay, so for example, let us say you're making a steel bridge. Okay, and so can you give me some examples? Where do you see steel bridges? Where do you see steel bridges?
Road crossing, railway crossing,
Huh? Railway crossing mean not
or
crossing really.
pedestrians.
So railways makes use of these bridges which are made out of steel structures. It makes extensive use of these kind of structures. Okay, so uh, so let us say there is a steel bridge, and you have a train which is passing over the steel bridge. So do you want, means would it be acceptable for the steel bridge to deform, deflect in any big way when the train is passing? It would not be
No, sir.
acceptable. Means in any structural application, you want a certain stiffness from your structure. So maybe you will say that, all right, when the train passes over the bridge, the maximum deflection at any point should not exceed more than 5 millimeters, or should not exceed more than 2 millimeters. So you have some loading in mind. So fine, so I have a train with axle load of 20 tons per axle. I have these many number of wheels which can be there at any point of time. There is a certain dynamic load factor which will come in, and for this loading I do not want the deflections to be more than 2 millimeters. So you come up with a stiffness requirement like that, and so that is one of the things that you're going to do. So you have a stiffness requirement. We call this as a stiffness requirement. There is a force, there is a deflection. Force divided by deflection is the stiffness. So you prescribe the stiffness. Second thing that you do is you impose a strength requirement. What is strength requirement? So stiffness requirement is, okay, when the train is on the bridge, by how much amount is the bridge deflecting because of the load of the train. So let us say it is deflecting by 1 millimeter. Now the train has passed away. Now after the train has left, is the bridge coming back to its original configuration, or is it staying in the deformed configuration by deformation of one, let us say deformation of 5 millimeters? Okay, now if this 5 millimeters is permanent, then what will happen when the next train comes? It may again deform, and you may have sagging in no time. Okay, so you do not want any kind of permanent deformation within your structure. So I also have a strength requirement. So what is a typical statement that we make for strength requirement if we do not want yielding? What is the simple statement that we make? We say that the von Mises stress in the material should not exceed the yield strength of the material. That is a, means fine. So we have a stiffness requirement and we have a strength requirement. So let us see as to how do we figure out as to which material would be a good choice uh, based on stiffness and strength requirement. Okay. Uh, all right. Now, now, uh, when we are talking about loading, what are the things that matter? So nature of loading is very important. Okay, So what are the different types of loading that you normally encounter? So if you take loading, okay, loading of a structure, what are the different types of loading that you encounter?
So tensile loading, bending loading.
So you can have tension or compression. You can have bending. You can have
Torsion.
torsion. Okay, so these are some typical loadings that we encounter. So what we are going to, so this is one thing. And then in terms of members, what kind of members do you commonly encounter? So if you, I told you this a little before, na? What is the form in which raw material is sold in the market?
43 का लगा लियो, काफी सारे कपड़े हैं, 15 मिनट में कैसे धुलेंगे?
Please keep your microphone on mute if you are not talking. So if you go to a hardware store, what is the shape in which you can buy the raw material?
In bars.
Round
You can buy it in the form of bars or beams. Okay, that is, bar stock is one kind of a thing you can buy. What else? Broadly speaking, we use either bar stock or we use sheets, material in the form of sheets or plates. Most of the structures that you take will use these two kinds of form of the material. So when we talk about bending, we are going to talk about bending of panels and bending of beams. Okay, when we say bending of panels or bending of sheets, it means the thickness of that is very small. Anyhow, so let us start with tension. So, so you have a bar with some section, okay? Area of the section is A. It is being subjected to some load and is of some length L. Now, in a given application, what will be fixed and what should be chosen, or what is given and what needs to be chosen?
Sir, can you please repeat it once again?
In a given application, so take that bridge and train example. What is given? What can be chosen?
Length is given, area should be chosen.
So
Length is
stiffness is
given.
also
Length is
given.
given. What else is given?
Stiffness.
Stiffness is given. What else?
Some material can be chosen.
Force is also given. Material can be chosen. And what else can be chosen? Cross-sectional area can also be chosen. Okay, so means so maybe, so let us say you are thinking of a column for the vertical column for the bridge. You have a bridge structure and it needs to be supported on columns, and these columns will be grounded to on earth. There will be some foundation in which these columns will be placed. So now the height of the column is fixed because you know what is the bridge you want to construct. So height of the column is fixed and the force is also fixed. Why? Because you know what is the load which the bridge is going to take. The force is also fixed. Stiffness is also fixed. You know what is the maximum deflection you want. But what can be chosen? Fine. What is the material you want to use for the column and what is the cross section of this column going to be? So cross sectional area is to be chosen. So now what are we saying? What is our objective? Our objective is to minimize the mass of this column. So for a simple straight column, what is its mass? Cross sectional area multiplied by the length, that is the volume, multiplied by the density. This is the mass of the column and we would mass of the bar, and we would like to minimize it. What is stiffness? How do you define stiffness in a simple manner?
Force by area. Force by
Not
length.
force
Sorry.
by area.
Force
Force
by length.
divided by
Deflection.
deflection. So if you have a cantilever beam, you are applying a force F, and if this is causing a deflection delta, then for this loading, the stiffness of the cantilever beam is F divided by delta. That is how you would define the stiffness. So what is F? F equals to stress into cross-sectional area, right? So this is sigma A divided by delta. What is delta? Delta is strain multiplied by the initial length, because strain is change in length divided by initial length. What is stress divided by strain?
Elastic
Young's
modulus.
modulus.
Elastic modulus. So that is the reason that stiffness is elastic modulus into cross sectional area divided by the length of the bar. Now, so mass, so what can I do? I can write down my area in terms of length, right? Area equals to SL by E. So mass, I can write it as A into, sorry, SL by E into L into rho. So finally, I can write mass as S into L square into rho by E. Now in this equation for mass, what is sort of, what will depend on choice of material and what will be fixed by the application?
The stiffness will be fixed and the
Stiffness
length
will
also.
be fixed. Stiffness and length are given. No choice over there. And what will depend on the choice of material?
The density
Young's
and the
modulus.
Young's modulus. Okay. So if you want to reduce the mass of this bar, which is being subjected to a certain force and for which you need a certain stiffness, so what is it that you should be looking at across different materials?
low
You should be
ratio of rho
looking
by E.
at rho divided by E. So whichever material has got the smallest ratio of density by Young's modulus, you would pick that material if you want to reduce the weight based on a certain given stiffness. Okay. Or you can look at materials with highest value of E divided by rho. So it is not simply the elastic modulus that you look at, but you look at elastic modulus divided by the density of the material if you want to reduce the weight. Now, in the same fashion, let us say there is a beam, okay, and for analysis purposes, a square sectioned beam is being considered. So height of the beam is B and width is also equal to B. And over here, it is being subjected to a load in the center. What do we call this kind of a loading?
Flexural load.
Bending load.
It's a bending load. What means, what do we call a beam which is being loaded in the center, free to rotate at the ends? It is a simply supported beam. Okay, so at the ends it is free to rotate and you're applying a center load. Now for this particular beam, we would like to minimize the mass. Now where will the deflection be highest?
At the point of
At the center.
At the center. Okay, now in this case, what is the mass? Mass is again cross sectional area into length into density. Cross sectional area in this case is B square. So B square into length into density. Now what is the stiffness? Stiffness is once again, so for a beam, uh, stiffness is F divided by delta. Okay, and L, what does deflection of a beam scale as? For a beam, how does it scale? The deflection as a function of force you are applying. You remember? For a cantilever beam, what is the tip deflection in terms of the force? It is PL cubed by what is it? It is, if I'm not wrong, I think it is PL cubed by 3EI or some constant into F into L cubed by EI. So F cancels off and the stiffness is basically some constant into EI by L cubed. Okay, where I is the second moment of inertia, which in this case will be BH cubed by 12 or B to the power 4 by 12. Okay, so this is the expression for stiffness, and using this relation you can write B square in terms of S, L and E. So once again, the mass expression for mass can be written like this. Over here, once again, stiffness is given, length is given, C is some constant. So it will be some parameter which is known multiplied by rho divided by square root of E. And this rho divided by square root of E will change from material to material. So when you are looking to reduce the mass of a beam, okay, so in that particular case, based on the stiffness constraint, you would be looking to select a material with smallest value of rho divided by square root of E. Next, let us say you have a panel. Okay, now let us say you have a panel. Everything remains the same, but now the bending moment of inertia is W into T cubed by 12. Now for a panel, what is known, what can be chosen amongst the dimensions W, L and T, what is known and what needs to be chosen? So let us give me an example of a panel.
Solar panel.
Uh, okay, solar panel is a panel, but it's not for structural applications. Take a car door, for example. Okay, so car door, you have a outer frame and then you put some sheet metal to cover that frame. Okay, now what is fixed and what can be chosen in this panel?
Length and width are fixed and the thickness can be chosen.
Very good. So length and width are fixed. Area is fixed. Okay. What you need to cover is fixed. What can be chosen is the thickness. So if you have a car door, you may say that, okay, if somebody pushes with 20 kg force, I do not want it to deflect by more than 2 millimeters. Okay. So 20 kg force divided millimeters is the stiffness that I desire for this car panel. So length and width is given and thickness can be chosen. Okay. So now once again over here, mass is width into thickness into length into density. So thickness can be written in terms of this stiffness. And finally, you can write expression for mass like this, where with means so where you get this factor of rho divided by cube root of E. So when you are selecting selecting panels, you need to select a material whose density divided by cube root of modulus is a smaller number. Okay, now I'll give you an exercise. Please do it now. You will have 5 minutes. So consider so you are looking at steel and aluminum alloys. Okay, you're looking at steel and aluminum alloys, and in a given application you have to reduce the weight based on the stiffness constraint. Okay, now amongst steel and aluminum alloys, which one will you pick if the if you have a bar and it is being subjected to tension or compression? If you have a square beam, solid square beam, it's being subjected to bending. And if you have a panel and it is being subjected to bending. In these three cases, which of the two materials will you choose if you have to reduce the weight? Start working. So what all parameters will you estimate? What do you have to estimate?
Sir, the density and the modulus.
Yes, but to minimize means to see which one will minimize. So you have to look at rho divided by E for a bar subjected to tension or compression, rho divided by square root of E for a beam which is subjected to bending, and rho divided by cube root of E for a panel which is subjected to bending. So you have to estimate these three parameters for steel and aluminum alloys. I did not tell you the specific variety of the alloy. Is that a problem?
No, sir, modulus is relatively constant.
Modulus is relatively constant. There is very little variation across the alloys for the density and the modulus. So please go ahead and estimate what will these three things be for steel and for aluminium. Rho by E, what will it be for steel? What will rho by E be for steel? So let density be in kg per meter cubed and let E be in, it won't, let E be in pascals. Okay. What will it be?
0.039.
Sir,
For what?
for bar it is approximately same.
For the bar, it is approximately the same. What is the number
So 0.037.
for steel?
In yes, like for a kg per meter cube, and then in GPA, the
Okay.
modulus.
Okay, fine. You have this in GPA. That's fine. It won't matter. Huh. What will it be for rho by? What is it for aluminium?
0.038.
0.038.
0.038. Okay, so steel wins by a very little amount. What will happen for a beam? What will happen for a beam?
0.54.
Hmm? What is density divided by square root of E for steel?
So 0.538 for steel.
Okay. And what is it for aluminium?
0.3227.
0.3227. Fine. Okay. And then for a panel, what will it be? What is it for steel?
1.312.
1.312. Okay. Aluminium.
So 1 second.
Aluminum
0.66.
is 0.66.
0.66. Okay. So what do you see now? Which would be a better choice of material if it is subjected to simple tension or compression? It won't matter so much. Both of
Yeah.
them appear to
Aluminum.
give you the same mass. But if
Mm.
it is a beam, which one wins?
Aluminum.
Aluminium wins if it is a beam by a good
And
amount. Like you can reduce the weight by about how much? Nearly some 40% odd you can reduce the weight. And if it is a panel, by how much can you reduce the weight? You can reduce the weight by nearly half. Okay. So aluminium, uh, so it is very interesting. Steel has got a higher modulus, but if you are imposing a stiffness constraint, then you can achieve the same stiffness at a much lower weight using aluminium as compared to steel. Okay. So in summary, uh, the thing I want you to note is that whenever you want to reduce the weight based on stiffness constraint, then you should be looking to minimize rho divided by E. If you are subjecting it to tension or compression, you should be looking to minimize rho divided by square root of E when you are subjecting a beam to bending loads, and you should be looking to minimize rho divided by cube root of E if you are if you have a panel which is being subjected to bending. Now, stiffness is one of the things that you are concerned about, and you can look to minimize the weight keeping stiffness at a certain desired level. The next thing is strength based design. Okay. So in strength based design, what is imposed is the constraint that the maximum stress in the material should not exceed the yield strength of the material. Okay. It should not exceed the yield strength of the material. So once again, so let's say take a beam. It is being subjected to tensile loading. The mass of the beam is cross sectional area into length into density. And what is the constraint equation now? The constraint equation is F divided by A equals to sigma y. Means at this or F divided by A must be less than sigma y. In the limiting case, it will be equal to sigma y. So what is A now? A equals to F divided by sigma y. Now, if you plug that, then expression for mass will be F into L into rho divided by sigma y. Now, in the expression for mass, what is given in an application? What will depend on choice of the material? What is given in an application and what will depend on the choice of the material?
Sigma y is given, rho will be dependent.
So rho and sigma y, the density and yield strength of the material will depend on the choice of the material, and the force and the length will be given in the application. So what should you be trying to minimize? Or when you are looking across different materials, what parameter will you try to minimize the weight?
Rho by sigma y.
You will be minimizing rho divided by sigma y if it is subjected to a tensile loading. Now let's take a beam. Now in a beam, what is the so once again the maximum stress would be equal to sigma y. What is the stress in a beam? How do you get the maximum stress? When a beam is subjected to bending, what is the expression for bending stress? It is my by I. So what is the expression for the maximum bending stress? It will be sigma max will be m into y max divided by I. So m equals to f into L by 2, y max will be equal to b by 2, and I is anyhow b to the power of 4 divided by 12. So from this expression, we can write b in terms of sigma y, and finally we can write m as equal to something in terms of L and f into rho divided by sigma y to the power 2 by 3. So we have to pick material with the smallest value of rho divided by sigma y to the power 2 by 3 in order to reduce the weight as per strength. And for a panel, we can go through the same exercise, and you can show that you have to minimize rho divided by sigma y to the power half in order to minimize the mass. So this is the summary slide. Okay, so for any given material, what will depend on the choice of the material will be its modulus, density, heel strength. Okay, and if you are choosing the material based on stiffness constraint, then you have to minimize these parameters. If you are choosing the material based on the strength constraint, then you have to minimize these. All right. Okay, so I end over here. Just give me a minute. I'll paste the form in the chat. What happened? Many of you seem to be very sleepy today. Okay, I have pasted the form in the chat. So please finish it. Try to complete it by 10 o'clock. I have fewer questions today. Any doubts you have, you can ask over the
Sir,
next 15 minutes.
it is not accepting responses.
I just enabled it. Are you logged in on Teams? It should be
So it's not accepting responses, sir.
Okay. I think the time, it will do now.
It's still not accepting.
It's still not accepting. What the hell happened?
It's accepting now, sir.
It is accepting now.
Just refresh it or select it again.
So where are the video lectures that you are recording being kept? Like if we want to.
It will be there in the general comment section. So if you go to.
So if it's possible, can you upload it as a file? Because the download from the comment section is quite buggy.
It's a lot of overhead for me every class. What do you want me to do?
So you can if you have a copy downloaded on your computer, can you upload it to the what's it called, the
Huh?
main group? Can you
It is
upload it
already
into the
there,
file
na?
section?
I don't understand. It is already there, so what is the point in me downloading and again uploading?
So we don't need to download then. We can just watch from there.
Where should I be uploading? Here on Teams.
Yes, sir. In the team, the files tab.
Acha, it plays it directly if I upload it.
Yes, sir. It plays directly.
Okay. Actually, I can give this assignment to a TA. Raunak, you are there? Raunak?
Yes, sir. Yes, sir.
Raunak, can you please take up this task? Even better, you do one thing, na? You can upload it on. You can fine. You can download it and create a folder called video lectures, and
Yeah.
just based on the day and the topic. Like for the questions, I'm saying, na, January 13th material selection. Like that.
Yeah.
In the same manner, you can say video title will be January 13 material selection, and day
Yes.
wise you simply upload it and place it in a folder
In Teams only.
in Teams only. Yeah, and
Okay, sir.
in
I'll
the
try.
files.
Yeah.
Okay.
Okay.
Thank you.